Okay, next lesson for Physics 12 coming up. This is going to be accounting for velocity while we're in orbit. Okay, so let's get going. All right, so we've already been looking obviously at things in space, right? So like talking about universal gravitation, gravitation between objects. Last lesson, or we talked about Kepler's laws. We've also now talked about how we can use those laws in some nice formula derivations with centripetal force and force of gravity to be able to calculate things like masses or heights of orbits and geosynchronous orbits and all that good stuff. Okay, what we're going to discuss a little bit more today is how we can again derive a separate formula, very similar, and use it to account for the velocity of objects that are in orbit. All right, so let's get started. So again, in that first unit, right, in our first chapter, we had talked about centripetal force, which is that center-seeking force that's pulling something into the center of motion, right, in that kind of idea of uniform circular motion. If we apply this idea to orbital rotations of planets, okay, yes, we know we talked about them being an ellipse, but they are slightly elliptical, and we can still use their idea of like circular motion for this concept, okay? And essentially that force of gravity, the gravitational force, is the same as the centripetal force in this case, right? So we see that that idea of Fc equaling Fg can be used to be able to find certain values, okay? So again, that centripetal force is that same force of gravity, right, connecting those two planetary objects, right, pulling them together. And we've got those two formulas there again that we've discussed, right? So centripetal force, right, that first one we had talked about in chapter 1 from unit 1 was that mv squared over r. You might recall in the last lesson we also used a formula similar to this of the Fc equaling Fg, but we used the other formula with like the 4 pi squared r. That version of the formula instead, okay? But in this one, because we are interested in the velocity, we're going to keep the mv squared over r in this case. And then, of course, our Fg that we talked about at the beginning, where it's the gravitational constant multiplied by the product of the two masses divided by the radius of the distance between them squared. Okay, so we can set up that first equation, right, by saying, okay, we know if Fc is equal to Fg, we get this. Okay, now the rest of the proof are on the slides, but I'm going to switch over again to the whiteboard just so you can see how exactly we get this, but they kind of get explained a little bit in the notes as well. Okay, so let's just switch real quick. Okay, so like we said, we're starting with that same assumption that our Fc is equal to Fg, right? The centripetal force in this case is the same as the force of gravity, right? Pulling these objects together. We are using, since we're wanting to deal with velocity here, we're using that our centripetal force is our mv squared over r, and our gravitational force is that gravitational constant multiplied by the two masses divided by r squared. Okay. Again, it's important to note that these two masses, right, m1 and m2, we can talk about m1 being the object that's being orbited, and then m2 being the object that is orbiting. Okay, so like you kind of make that little note there. It's kind of like m2 is orbiting, right, and m1 is the center, I guess, if we want to call it that. Okay, so that means when we talked about the centripetal force here, it's the mass of the orbiting object, so that would actually be m2, right? So these masses would be the same. And then because there's one on both sides, they can cancel, right? So that simplifies our equation a little bit. Then we can cross multiply like we did before, right, in our derivation from the last lesson, where we have v squared r squared is equal to g m1 r, right? Again, you've got an r on both sides, so this r can cancel with one of these. And then again, because we're interested in velocity, we can get v squared is equal now to gm1 over r. Okay, so that's where we can get to. But what if we, again, what if we don't know the radius, right? How will we solve this, right? So if we don't know the actual radius between, or, say it's a question where we're trying to find what's the height, the altitude of whatever this orbiting object is, we're going to need to make kind of a justification there, right? A little bit of an edit. So we go back to that same formula we were using before, which was that idea where that velocity was equal to 2 pi r over t. okay? So we can take that, do a little rearrangement there to be able to substitute it in here for r, okay? That way, all we need to know is the period of the rotation, and we actually don't need to know what the radius is, and that velocity will fit with our velocity here, and we'll be able to combine, okay? So a little rearrangement here, what we get is that Vt is equal to 2 pi r, so Vt divided by 2 pi is equal to r here. This then can get substituted in here, right? And what we get is v squared is equal to g m1 all over Vt over 2 pi, right? Do a keep switch flip there with your fractions, and then what you get is actually, and I'm going to need to erase this because I'm running out of space. So let's start at the top again. Right. So again, what we can do is we can keep switch flip this fraction and have v squared is equal to g m1, and then you're multiplying by 2 pi over Vt. So what that then gives you is v squared, and this is a nice single fraction of g m1 2 pi over Vt. And then because these are both v's, you can multiply both sides by v and actually get v cubed is equal to, you can probably put this out front because it's more of a coefficient, 2 pi g m1 all over t, right? And remembering that your m1 was the mass of the center object, right? So the mass of the object you're orbiting around. So like if it's orbiting around Earth, this would end up becoming mass of the Earth, right? If we're orbiting around the sun, this would end up being mass of the sun, and we can use all of our constants to figure that out, okay? So that's again going to be a formula that we're going to use to help us with calculating our velocities. All right, back to our notes. Once I get my cursor, here we go. Okay, so again, the slides that are here walk through that kind of formula again, right? So it shows that derivation. So for those of you who weren't able to watch the video, which you obviously can't hear me if you're not watching this video, but whatever. If you're just accessing the slides, right, you kind of see that same derivation with some explanation, right? So you're starting with that whole Fg is equal to Fc, right? The mv squared over r, gm1 m2 over r squared, right? We're stating what each of those things are. We, you get that your m2 cancels on both sides. You use that v is equal to 2 pi over t, which gets rearranged to give you this for r, gets substituted back into here, giving you the following, which then gets nicely rearranged to your v cubed is equal to 2 pi g me over t. Again, that me is assuming that something is orbiting around the Earth, right? Because the mass used in this formula is the one that is of the center object, the thing we're orbiting around, okay? All right, so once we have the formula, we're allowed to solve problems with it, okay? So we're going to have slightly different problems, but let's go with it. I'm going to try and make this video a bit shorter. We're just really going to do one type of example and then kind of see how well we were able to go there. Okay, so what this can be done is that we can use our formula now to be able to calculate velocities, which then can allow us to calculate particular masses if we need them, or we can calculate heights, all that good stuff. Okay, so just manipulations of formulas as we need them. Okay, so let's take a look at this here sample problem. Right, so what we've got is at what velocity and altitude must a satellite orbit in order to be geostationary? So remember, we did talk about geostationary or geosynchronous in the last lesson. It means that something is orbiting at the same time that the Earth is rotating on its axis, so it appears as though that particular object that's in orbit appears to never move. Okay, so let's take a look at what we're dealing with here. Okay, so again, we're trying to find velocity, altitude of a satellite in orbit to be geostationary. Okay, so again, that does imply that we're dealing with the Earth here. So when we go to set up the things that we know, right, since we're geostationary around the Earth, we know that the time it takes for that satellite to orbit is 24 hours, okay, which can then be done into seconds, right? So you multiply that by your 60 minutes a day times your 60 seconds per minute, and you get your value of 86,400 seconds, okay? Other things that we know is we do know the mass of the Earth, right? The object that we're rotating around, that's going to be needed for our formula there, which is our 5.98 times 10 to the 24 kilograms. Again, that's coming from your constant sheet, okay? Something else that's going to be helpful later is the radius of the Earth, right? Because we're being asked in a part of the question for what is the altitude, right? We won't need that just yet though, so I'll kind of come to that when we need it. Okay, so recall that the formula we just derived, and we were looking for the velocity to start, but the formula we derived involved that idea of velocity, right? We just came up with v cubed is equal to 2 pi g m1 over t. The only variables in this formula are the mass of the object you're rotating around and the time it takes for the rotating object to complete one full rotation. Right? So because it's geostationary, this is the same as the rotation of the Earth, right? And because m1 is our object that we're rotating around, it's the mass of the Earth, which can be used here. This just becomes a pretty basic plug and chug formula, okay? So we get v cubed is equal to 2 pi, our gravitational constant of 6.67 times 10 to the minus 11, multiplied by our mass of the Earth, which is here, at our 5.98 times 10 to the 24 kilograms, divided by our time, 86,400. Okay, and that's what we're dealing with. So this just becomes a plug all of this very, very carefully into your calculator. We get that v cubed should end up equaling something along the lines of 2.9006 times 10 to the 11. Okay, and then you would cube root that value there, and you get a value of 3.07 times 10 cubed, and the units here would be meters per second. Okay, so I think I end up getting like 3,072.54 meters per second when I did all this in my calculator, but of course we're dealing with only three sig figs here, right? 1, 2, 3, 1, 2, 3, so we get 3.07. Okay, so there's our velocity of our geostationary object, right? So if something's going to be geostationary, it needs to be moving at that speed in order to stay geostationary, okay? So again, the next part of the problem is, well, what's its altitude going to have to be as well, right? How high above the Earth must it be, and how fast must it be going in order for it to be geostationary? So we've got one, let's go for the other. So remember, in our last video, we also defined a formula for geostationary orbits, okay? So our formula we talked about in the last lesson for geostationary orbits was the following, where we had that 4 pi squared r m2 over t squared was equal to g m1 m2 over r squared. Okay, that was the formula we were using for geostationary orbits. We again saw that these values canceled, with m1 again being the mass of the object that we're rotating around. So in this case, that would be the mass of Earth. Okay, you can again manipulate that formula, right? You do your cross multiplication, you get 4 pi squared r cubed, those have canceled, equals g mass of Earth times the time squared. We're again interested in the altitude, so if we can find the radius, right, between the center of the Earth and the object, we can then subtract the radius of the Earth to get the actual altitude, okay? So at that point, we're looking for r, so we can say r cubed is going to be g times, I'm just going to start plugging in my actual numbers at this point, mass of the Earth, which is my 5.98 times 10 to the 24, multiplied by my time, which is my 86,400 squared, divided by the 4 pi squared, okay? So you would calculate that, right, the g being 6.67 times 10 to the negative 11, multiply that all out, divide it by your 4 pi squared, you end up getting, and then cube rooting it, okay? So you end up getting a value where r is equal to 4.225 times 10 to the 7 meters. Okay, so now that's the radius that you're going to get, right? Because it's the radius from the center of the object being orbited, right? So the Earth in this case all the way to the actual height of the object. So that would mean that we'd have to take this value here and subtract the radius of the Earth to actually get to see, well, how high above the surface of the Earth is the satellite itself, okay? So we have to take this value and subtract the radius of the Earth, right? So it's essentially like our height is equal to this radius minus the radius of the Earth. This is our value for our radius, which is 4.225 times 10 to the 7 meters. Radius from the Earth is going to come from our student reference sheet, which ends up being 6.38 times 10 to the 6 meters. We do that subtraction, and we get a value here of 3.59 times 10 to the 7, once you account for sig figs. Right? So the velocity of our geostationary satellite needs to be 3.07 times 10 cubed meters per second, and its altitude needs to be 3.59 times 10 to the 7 meters above the surface of the Earth in order for this to all stay where it needs to stay. Okay? Now, the other thing I did want to mention with this, though, is I went back and we used the formula that we had talked about with the geostationary orbits. However, because we actually had the velocity, another option that we had was to actually just go back and use our wonderful little velocity is equal to 2 pi r over t formula to solve for r, right? We could have taken the velocity that we calculated, right, as that 3.07 times 10 cubed, so I'd probably use the extra decimal place right before we rounded for sig fig, since we're going to be substituting it again here. We rearrange this formula, we get that Vt is equal to 2 pi r, so Vt divided by 2 pi will give us our r value, right? We solve for the velocity, we could plug into this, right? We don't have to mess around with the gravitational constant or the mass of the Earth, like things that are a lot messier to deal with, right? And then instead we can use that velocity of 3.073, I guess if we were going to keep that extra decimal place, right, times 10 cubed multiplied by our time of that 86,400 seconds divided by our 2 pi, right, and that would equal our radius, and we end up getting that exact same value of that, like 4.225 times 10 to the power of 7 meters, right? And then we do the same thing, we subtract the mass of the Earth and we get the same value, okay? So either way, it works, okay? So that's just another way to think about it. If you like this better, once you have the velocity, you can use that formula instead of having to go back and use the one that we defined for geostationary orbits, okay? So just taking it a bit at a time, that's essentially it for this little sub-lesson, right? So, I mean, that's the full, like, it was one of the examples from the textbook. That's the full one that's there if you want to kind of see it again, but ta-da, okay? And just a couple practice questions specifically on that, right? Finding velocities, as well as altitudes of particular moons or satellites. Okay, you'll see that in 17 you are being actually asked to find the amount of time something happened. So again, it's just a different rearrangement of the formula that we've been dealing with. You'll be given different variables to be able to substitute. Once again, if stuff is tricky and you're not sure what's going on, the full solutions to this will be posted, not just the answers here. And you can always shoot me an email or request a Google Meet Hangout for us to talk about it in detail. I apologize, I forgot to, in my PowerPoint, go and fix these little decimals and put them as brackets, so just remember that that's a bracket there, and the answer is just 7.42, not 15.7.42. My bad, sorry, I'll fix that for next time. Okay, so we'll just kind of call it there. Another quick little lesson done, and we'll do one more kind of lesson on escape velocities. And then that kind of finishes up this unit. All right, so we'll kind of get going here. Okay.